This is about Chapter 9, the second half, dependent samples. Now when we started Chapter 9, the first half we did independent samples. Independent samples, we just had two separate samples, and there's absolutely no relationship between the members of one sample and the members of the other. This time we're going to talk about dependent samples, where not only can each data value be paired with another data value in the other sample, if you don't do that, you're kind of missing the point. So let me skip over a couple of slides here and look at just the data as we describe this. You have the other slides, you can read over it, and this information is actually right there on your note sheet. But if we look, the situation we have here is we have a list of patients who were told that they were going to have, I think it's open heart surgery. Now realize I have the completed slide here, so you don't have this last column filled out yet. Just hold your horses and listen to the scenario. Okay, so these people are told that they have a heart condition, and then with wonderful amounts of love, they're given an anxiety test. The higher the number, the higher their anxiety. So right here, this column is the score they made on that anxiety test after being told about the heart condition. Okay, then they gave them counseling. And when they gave them counseling, the idea of the counseling is to reduce the anxiety. So after the counseling, they gave them the anxiety test again, and that second column is how much anxiety they seem to have after the counseling. Alright, so this data is paired data because we have Jan's anxiety level before the counseling, Jan's anxiety level after the counseling. Now, we're not going to look at the first list of scores or the second list of scores. What we're interested in is this third column called the difference. We just want to know how much their anxiety level changed. I don't care what the number was before. I don't care what it was after. What I want to know is how much did the anxiety level change. So when we're doing dependent samples, we're going to be given these first two columns of data. This column that says difference is not going to exist. That's the part you have to read the problem and decide this is what I need to make. A difference column. You're going to need this data put into your calculator. So, let me erase some of my mess here, and let's start from the beginning again. I look at my data and I see that it is paired data, which means I want Jan's score before, I want Jan's score after. I want to find the difference. This data is all going to go into L1. I just need to subtract to find how much her anxiety changed. So I do 121 minus 76 is going to equal that 45. Now I can do that on the home screen, and I can sit there and write all these down and then go to L1 and type them in, but I'm doing extra work by doing that. I need to go straight to L1, and in L1 I need to type in 121 minus 76, hit enter, and it'll do that math for you. And then 93 minus 93, and so on. But you always want to make sure you're doing the first column minus the second column to get the answers over here. That list of data at the end is the only thing we're going to do a hypothesis test on. Might want to pause this so you can get the data into L1, because then we have to talk about how to do the hypotheses. If the counseling or whatever the question's asking you about doesn't change anything, then that means if I look in my two columns, I would have the same number. The same number before and the same number after means the counseling didn't do anything. And that gives me a difference of 0. 0 means whatever it is you're measuring made no difference whatsoever. 0 is the number we use in our hypothesis test. The mean equals 0 is always going to be our null hypothesis. That's a 0. The null hypothesis is always the mean is equal to 0, because that means there's no difference. The alternate hypothesis is either going to be a greater than, a less than, or not equal to. In this claim, we want to know specifically if the counseling reduced anxiety. Find an example where that worked. If the anxiety was high, and then it went to low, high anxiety, then we went to low. If I had a big number minus a small number, I ended up with a positive answer. A positive answer means mu is greater than 0. What if it went the other way? If my anxiety level went up, it gave me a negative answer. That's mu is less than 0. Now, not equal to is only when you're not looking for one specific direction. If it just says, does it make a difference or not, then you use not equal to. That doesn't happen a lot. Usually you want to know which direction things have changed. So the question is, mu equal to 0 means nothing changed. Which one of these two says the anxiety went down? Anxiety went down up here with Jan, didn't it? High minus low gave me a positive answer, so my alternate hypothesis is going to be with a greater than. You want to be careful with that, because even though the sentence says reduce anxiety, reduce doesn't mean less than. It's the sign of your answer that tells you how to write the hypothesis. Now when I go to the next page, it shows the hypotheses typed out. Notice this little subscript of D. That's just to say that it's not for the before column, it's not for the after column. This is the mean for the difference column. I believe that's the notation used in the book. Remember, you're not going to have to write these out. You're going to have to match them, both on StatLab and on the test, because it's all multiple choice. These are always t-tests. Not two sample t-tests, because I just put in one list of data. One list of data is just going to be a t-test. So we already have the differences in L1 if you followed along with me. So we do a t-test and we put in our information. The number, well, first of all, since we have data in L1, change your input to data, not statistics. The number in the null hypothesis is 0. This is, you're just telling it what list you put the data in. And then make sure you pick the correct symbol. When you calculate, you get a p-value of 0.001. That's less than 1%, which tells you to reject the null. Since the claim is the alternate, we're going to support the claim. Now, I would pause this and see how far you can get on the other example before moving on. with the recording. Use the recording to check yourself. This time we have experimental twins. They play with educational toys. The control twin just plays with regular toys, only for a couple of hours a week. And we want to know if the educational toys help the experimental twin read at an earlier age. So these are the reading ages of the twins in months. Always do your subtraction, first one minus second one. Can you do the problems the other way? Yes, you can. But if you do the problems the other way, it's not going to match the symbols that you want to have for your hypotheses. Your p-values are going to be different because you're going to be doing the problem kind of backwards. So since you have to play matchy-match, play nice. Always do first column minus second column. That data goes in L1. To find your hypotheses mu, the null is always equal to 0. I want to know if the experimental twins read earlier. If I find an experimental twin who reads earlier, the answer that I got here was negative. The symbol that I used to say negative answer is what works is less than 0. So when I look here at my two hypotheses, the null is always equal to 0. Less than 0 is the claim. Put the data in L1. We already did that. We do a t-test. Make sure you changed your symbol here because that'll change your p-value dramatically. And I end up with a p-value of 0.023. That's less than alpha, so we reject the null. And again, we support the claim because the claim is the alternate.